Welcome to this video on sample spaces and discrete probability distributions. Let's begin. The purpose of this video is to connect previous concepts with new concepts. In a previous section, you learned how to create a sample space for an event. Recall that a sample space is a list of all possible outcomes for an event. In this video, you will learn how to create a discrete probability distribution from a sample space. This will lead you to an understanding of why the binomial formula is needed. In this video, you will learn how to create a discrete probability distribution from a sample space and explain why the binomial formula is needed. Should you take the bet? Suppose you and your friend make a bet. You roll 2 fair 6-sided dice. If exactly one die results in a 1, your friend will give you $5. Otherwise, you have to pay your friend $5. What is the probability that you will win? What is the probability that your friend wins? Are the odds in your favor? Should you take this bet? So before we get into that, let's do a much simpler example where we just flip a coin twice. So the reason I'm picking this experiment is because it has a much smaller sample space. So pause this video and write out the sample space for flipping a coin twice. In other words, list all the possible outcomes. So the 4 outcomes are heads, 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 tails, tails, heads, tails, tails. So the sample space, often we usually use a single letter number to represent each outcome. In this case, we're using H to represent the outcome of heads and T to represent the outcome of tails. So the sample space is HH, HT, TH, and TT. So from here, what we want to do is we want to create a probability distribution. So what is the probability of each of these 4 outcomes? Well, we would say that they're all equally likely. After all, we don't have any reason to think that one outcome is more or less likely than the other, and we're assuming that we're flipping a fair coin where heads and tails are both equally likely. So this sample space lists all of the permutations. Permutations mean that order matters. In other words, we are saying that the outcome of first getting heads on our first flip and then tails on our second flip is different from getting tails on your first flip and getting heads on your second flip. But what if I don't care whether I get heads first or second? Rather, what if I simply want to know the probability of getting heads exactly once in 2 coin flips? Well, what I can do is I can change my list of outcomes to what's called a discrete probability distribution. So if I get heads twice, right, that represents this line right here. So I'm getting heads twice in 2 coin flips, and as you can see, the probability is 0.25, so that just carries over. And then both of these outcomes, heads and then tails, tails and then heads, represent getting heads exactly once. So to figure out that probability, I simply add 0.25 to 0.25, and I get 0.5. And then last but not least, getting heads 0 times, which means I get 2 tails, is also a probability of 0.25. So from our sample space and the associated probabilities with each outcome, I have created a discrete probability distribution. So when I go from my list of my sample space, where order matters, to a discrete probability distribution where order doesn't matter, I have created what's called a random variable. And in this case, my random variable is defined as the number of heads. I could have just as easily defined my random variable as the number of tails, and I would have gotten a similar result. So now that we've had this practice, let's go back to our original question about our bet. So let's think about the sample space involved in this bet. We're going to roll 2 fair 6-sided dice. So how many outcomes are there? How big is our sample space? Well, the sample space of rolling 2 dice can look like this, or I prefer the visualization where I can actually see all 36 possibilities. So let's define success as rolling a 1 and define failure as rolling any other number. So from this sample space of 36 outcomes, we want to generate a discrete probability distribution, and our random variable we're defining as the number of 1s rolled in 2 die rolls. So the easiest one to think of or figure out is rolling 2 1s, right? Snake eyes is what we call it. So there's only one way that this can happen out of 36 total outcomes, all of which are equally likely. So the probability of this is 1 over 36. So now we have that filled in. Now let's think about what is the probability of rolling exactly 1, 1. So now let's figure out which outcomes are represented in that set. So I could get a 1 and a 2, 1 and a 3, 1 and 4, 1 and 5, 1 and 6. I could also get a 2 and then a 1, a 3 and then a 1, 4 and 1, 5 and 1, 6 and 1. Count those up and you get 10. So we have 10 outcomes out of a total of 36 that result in getting exactly 1, 1 in 2 die rolls. Okay, so now, last but not least, we have the rest, which is not getting any ones. So that's this highlighted portion here, and you can count them individually, or you can say it's 1, 2, 3, 4, 5 by 1, 2, 3, 4, 5, and that's simply 25 over 36. So I have quite elegantly used this sample space of 36 equally likely outcomes to generate a discrete probability distribution. So now I have all the information I need to determine what is the likelihood that I win that bet. So let's use the discrete probability distribution that we generated to answer this question. So what is the probability that you win? Well, remember, the conditions for you winning is that you roll a 1 exactly once. And as you can see from the table, the probability of that is 10 over 36, which is about 28%. In other words, you win about a quarter of the time. But what about your friend? Well, your friend wins if you roll a 1 either 0 times or 2 times. So to find that probability, we just have to add the probability of each event together. So we have 25 over 36 plus 1 over 36, which is 26 over 36, or about 72%. So let's think about it. You win about 28% of the time. Your friend wins about 72% of the time. So what do you think? Should you take the bet? Probably not. So the question on your mind might be, how does all of this relate to the binomial formula? After all, at the beginning of this video, I promised that I would use all this information to help you understand why we need the binomial formula. So the binomial formula looks like this. It's a little bit scary. You may not have even ever seen an exclamation mark in one of your formulas before. And we have a lot of variables. N is the number of trials, X is the number of successes, P is the probability of success. So why do I need this complicated formula to find the probability? Why can't I use one of those very simple equations or formulas that we used back in the probability chapter? Well, why? Let me tell you why. What we need to do, and what this formula is doing for us, is it's calculating on this side the number of different ways or permutations that an event can occur. So this is what we did when we created our sample space. Now when we have small sample spaces, we can do this manually, but if you have a sample space that's hundreds or thousands or even millions of outcomes big, then you can't list the sample space. That would just take forever and ever. So that's what the binomial formula is doing on this side. It's telling you the number of different ways an outcome or an event can occur. And then over here, the right-hand side of the equation is telling us the probability of each of those outcomes. So why do we need the binomial formula? It takes into account all the different ways an event can occur, as well as the probability of each way. For example, there are many different ways in which I can roll exactly 1, 1 when rolling 2 dice. We saw that by looking at the sample space. I must consider each way or permutation and sum the probabilities of each outcome in order to find the probability of getting exactly 1, 1 when rolling 2 dice. With smaller sample sizes, as I mentioned before, it is possible to calculate the probability without the binomial formula or statistical software. We can just list the sample space and then create our discrete probability distribution like we did in the 2 examples in this video. However, as the sample space becomes larger, it becomes harder and harder to generate the sample space and list all the different ways an event can occur. The binomial formula or statistical software is a shortcut. Now that you've watched this video, you should be able to create a discrete probability distribution from a sample space and explain why the binomial formula is needed.